Let's solve some more of these systems problems. If you remember, there's a hard way to do this and an easy way to do this. The hard way is to solve Newton's second law for each box individually and then combine them, and you get two equations with two unknowns. You try your best to solve the algebra without losing any signs, but let's be honest, it usually goes wrong. So the easy way to do this, the way to get the magnitude of the acceleration of the objects in your system, that is to say, if I want to know the magnitude at which this 5 kilogram box accelerates or that this 3 kilogram box accelerates, all I need to do is take the net external force that tries to make my system go, and then I divide by my total mass of my system. This is a quick way to get what the magnitude of the acceleration is of the objects in my system, but it's good to note it'll only work if the objects in your system are required to move with the same magnitude of acceleration. And in this case, they are. What I have here is a 5 kilogram mass tied to a rope, and that rope passes over a pulley, pulls over, and connects to this 3 kilogram mass, so that if this 5 kilogram mass has some acceleration downward, this 3 kilogram mass has to be accelerating upward at the same rate. Otherwise, this rope would break or snap or stretch, and we're assuming that that doesn't happen. So this rope is the condition that requires, the fact that this rope doesn't break is what allows us to say that the system is just a single big total mass with external forces exerted on it. So how would we solve this? I'd just say that, well, what are the external forces? Keep in mind, external forces are forces that are exerted on the objects in our system from objects outside of our system. So one external force would just be the force of gravity on this 5 kilogram mass. So I'm going to have a force of gravity this way, and that force of gravity is just going to be equal to 5 kilograms times 9.8 meters per second squared, because that's how we find the force of gravity. Should I make it positive or negative? Well, this 5 kilogram is going to be the one that's pulling downward. So if the question is, I hold these masses and I let go, what's the acceleration? This 5 kilogram mass is going to accelerate downward. It's going to drive the system forward. That's the force making the system go. So I'm going to make that a positive force. And then I figure out, are there any other forces making this system go? No, there are not. You might say, well, what about this tension over here? Isn't the tension on this 3 kilogram mass, isn't that tension making this system go? Not really, because that's an internal force exerted between the objects in our system, and internal forces are always opposed by another internal force. This tension will be pulling the 3 kilogram, trying to make it move, but it opposes the motion of the 5 kilogram mass. And if we think of this 3 plus 5 kilogram mass as a single object, these end up just canceling on our single object that we're viewing as one big 8 kilogram mass. So those are internal forces. We don't include them. They're not part of this trick. We have to figure out what other forces would try to make this system go or prevent it from moving. Another force that tries to prevent it from moving is the force of gravity on the 3 kilogram mass. Or one force that tries to prevent the system from moving would be this force of gravity. How big is that? That's 3 kilograms times 9.8 meters per second squared. And that's trying to prevent the system from moving. This 5 kilogram mass is accelerating downward, and this force is in the opposite direction of motion. That trips people out sometimes. They're like, I don't understand. They're both pointing down. Shouldn't they have the same sign? They would when we're using Newton's second law the way we usually use it, but when we're using this trick, what we're concerned with are forces in the direction of motion. This is an easy way to figure it out. Forces in the direction of motion we're going to call positive. And any forces opposite the direction of motion we're going to call negative. So forces that propel the system forward, we'll just call that the positive direction. Forces that resist the motion, we're just going to call that the negative direction. And since this is on this side of the motion of the system, everything in this system is going this way. The 3 kilogram mass goes up, the string over here goes up, the string up here goes to the right, the string right here goes down, the 5 kilogram mass goes down. Because all the motion in the system is this way, we define that way as positive, but this force of gravity on the 3 kilogram mass is the opposite direction. It's opposing the motion of the system. It's preventing the system from accelerating as fast as it would have. That's why we subtract it. And now we just divide by the total mass, and the total mass is just 5 plus 3 is going to be 8 kilograms, and I get the acceleration of my system. So if I just add this up, I get 2.45 meters per second squared. So this is a really fast way to get what the acceleration of our system is, but you have to be careful. If the question is what's the acceleration of the 5 kilogram box, Well, technically, that acceleration of the 5 kilogram box would be negative 2.45. What we really found here, since we were just finding the magnitude, was the size of the acceleration. Since this 5 kilogram box is accelerating down, and we usually treat down as negative, you won't want to forget that negative in putting in that answer. The acceleration of the 3 kilogram box, however, would be positive 2.45 meters per second squared. So when you're applying this to an individual box, you have to be very careful and make sure you apply that acceleration with the correct sign for that particular box. And if you wanted to find the tension now it's easy to find the tension. I could find this tension right here if I wanted to. If the next step was find the tension in the string connected to the boxes, now I can just use Newton's second law, but the way we always use it. I'm done with the trick. The trick is just a way to get the magnitude of the acceleration. Now that I have that, I'm done treating it as a system or a single object. I'll look at this single 5 kilogram mass all alone, and I'll say that the acceleration of the 5 kilogram mass, which is Newton's second law, is going to equal the net force on the 5 kilogram mass divided by the mass of the 5 kilogram mass. I know the acceleration of the 5 kilogram mass, but if I'm going to treat up as positive now, I got to plug this acceleration in with a negative sign. So negative 2.45 meters per second squared is going to equal the net force on the 5 kilogram mass. I've got tension up, and you might be like, wait, we said that was an internal force. It was an internal force, and we didn't include it up here, but we're doing the old rules now. Normal, second law in the vertical direction. So I use vertical forces, and if they're upward, I'm going to treat them as positive. And if they're downward, like this 5 times 9.8, I'm going to treat it as a negative because it points down. 5 times 9.8 meters per second squared. And I divide by the 5 kilogram mass because that's the box I'm analyzing. I'm not analyzing the whole system. I'm just analyzing the 5 kilogram box now. And I can solve and I can get my tension. The alternate way to do this would be to say, all right, let's just treat down as positive for this 5 kilogram mass. I'd then plug my acceleration in as positive, and I'd plug my force of gravity in positive. Then my tension would be negative. I'd get the same value. Now here I'm just solving for the magnitude of the tension anyway. So if I solve this, if I plug this into the calculator and solve for tension, I'm going to get 36.75 newtons, which is less than the force of gravity, which it has to be, because if the tension was greater than the force of gravity, this 5 kilogram mass would accelerate up. We know that doesn't happen. The tension's got to be less than the force of gravity so that this 5 kilogram mass can accelerate downward. So that's a quick way to solve for the magnitude of the acceleration of the system by treating it as a single object. We're saying that if it's a single object or thought of as a single object, which we can do because these are required to have the same acceleration or same magnitude of the acceleration, then if we're treating it like a single object, only external forces matter, and those external forces that make the system go are going to accelerate the system, and those external forces that resist the motion are trying to reduce the acceleration, and we divide by the total mass of the system that we're treating as one object, and we get the acceleration. If that still seems like mathematical witchcraft, if you're not sure about this whole idea, I encourage you to go back and watch the video. We solved one of these types of problems the hard way, and you see you really do end up with the force that tries to make the system go externally, and the external force that tries to stop it divided by the total mass gives you the acceleration. Essentially, what we're saying is that these internal forces cancel if you're thinking of this system as one single object, because these are applied internally and they're opposed to each other. One tries to make the system go, one tries to make the system stop.